All right, welcome back. It's a big day. We are going to do what we've been waiting for. We are going to treat this derivative like a function. So, quick review. In the past, even the last section, we had a function, like f of x equals x squared. And then we'd ask something like, what is the derivative when x is 1? And we'd say, well, that means that there's some kind of a tangent line with a slope, and it touches my graph at x equals 1, in this case also at y equals 1. And we basically computed that tangent line. The formula we had with the f of a plus h minus f of a was the change in the y values, and the h was the change in the x values, and we said, what is this slope? But every single different point on here is going to have its own tangent line, or at least almost all of them for most functions. And they're all going to have their own slopes, and I would rather not compute them individually. In fact, if every different x value has its own slope, that means there is a function, something that goes from an x value to the slope of the tangent line, and that is our derivative function. Talking about that will give us a lot of power. It'll save us a lot of time, and we can start asking questions of the derivative that normally we would ask of functions themselves. So let's think through this. Well, last time we had a definition for a derivative, and we said, okay, f prime, and before we said of some number, now we're going to say of x. And this, my friends, is how you make a formula. You do what you would have done otherwise, and instead of plugging in a number, you just leave an x or some other variable. So let's make a formula for a derivative. And it looks a little bit like this. We still want my h's to go to 0. We still want the change in the x value to be an h. And we're still going to want a change in y values. Okay. But now instead of a plus h, we're just going to do x plus h. And we'll figure out what x is later. That's it. Not a big change, just a real small one. Those a's turn to x's, and now this thing is a function. We do it in 2 steps because there's just a lot of letters flying around in this definition. But that's it. That is our amazing definition. You should commit that to memory. On my deathbed, I could probably still tell you the definition of a derivative. Better done with an example. Let's take a look. So if g of x is equal to the square root of x, and I want to know what is the derivative function for g. A definition using a limit. It looks a lot like the same as before. A lot like before. But now, instead of plugging in a number, I'm going to say plug in x plus h. And again, plug in x. So no matter what x value I'm at, that numerator is still going to be the change in the y values. Fantastic. That's it. All we have to do to be able to use this to know the derivative of square root of x for now and forever is to work through this limit. So we'll do it once now, and then you will always know the derivative of a square root. Maybe you know how. This should look familiar. This is definitely going to be one of those conjugate games. So I'm going to multiply the top and the bottom by this conjugate in the hopes that we can deal with some of those square roots. Always got to do the top and the bottom by the same thing to make sure we're really multiplying by 1. Also notice, by the way, that if you were to plug in h equals 0 before, you would get 0 over 0, which is our cue that we should do a bit more work to clean this up. Okay, I'm pretty good at multiplying conjugates at this point, so I'm going to do it in one step, knowing how they FOIL out. They basically just get rid of those square roots. And then on bottom, we need to be careful using some parentheses, because that h is going to multiply that entire conjugate. Very nice. All right. Well, that top cleans up quite a bit. We can definitely get rid of those x's. You might even be able to do these next 2 steps in one step as you get more confident. I usually will, but we'll go slower this time. Oops. Okay, so next up, looks like those h's are going to cancel. Careful now, what's left behind on top is a 1. So, all we have now is a limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. And the thing to notice is now that nothing bad happens if I plug in that 0. So I'm allowed to plug it in, and that's how I take this limit. This function is continuous at h equals 0. So this is just 1 over the square root of x plus the square root of x. I think I can do better than that. That looks like 1 over 2 root x. Nice. That's it. That is the derivative of the square root of x. And from now on, if I wanted to know the slope of the tangent line when x is 5, I could just plug in 5 into that function. Just for completeness, let's go ahead and point out that I could rewrite this with the 1/2, and I could write this as an exponent. So x to the, and it looks like there is a square root, so I'm going to need a half, and it's in the reciprocal, so I need a negative. So 1/2 x to the negative 1/2. I'll usually write it as the way on the left, but both are fine. We're not going to really worry about rationalizing that denominator either right now. There is another thing that's being asked in this problem. What's the domain? Worth pointing out, the domain of my original function is that x is greater or equal to 0. This is actually a little bit more restrictive. My domain is going to be, well, it's got a square root, so x has to be greater or equal to 0, but also it's in the denominator, so x can't be 0. I don't want to divide by 0. So I get the same domain as before, except for that I can't have 0. It's actually a little bit more strict. And maybe that makes you feel good knowing that there isn't a derivative at the end point of a graph that looks kind of like that. So there's no derivative at that endpoint. Right? There's my square root. Super neat. A lot of what we're going to do in the next section or 2 or 4 is try to pre-compute a bunch of these derivatives so that we don't have to do these limits. You still should be able to. Very likely that something like this will be on a test where you have to use that definition. But as we move forward, we'll get faster and faster, and we won't have to do these by hand. Okay, next video, we'll do a quick application of how handy it is to have this derivative function around.